Okay, so we are in video lecture 17, and this is exactly where we left off in the last lecture. So we understand there is a way to find out that coexisting minerals, if they are in equilibrium, thermal equilibrium, they can be found out by doing this little exercise. If they correspond to a single straight line, which is essentially corresponds to a particular temperature, for which this term is a constant. So compositions lying on this rock, on this line, would have equilibrated at the same temperature. But in this diagram, if the coexisting compositions are distributed this way, that means they have not been equilibrated at the same temperature condition. Instead, the equilibration has been over a wide range of temperature. The reasons for this we don't discuss at this point of time. Now there is a few other things, but you know we did not discuss this term. I will just clean up the board a bit. The important point here was, I think, I'm doing it from memory, I hope I'm right. So we are doing it for reaction 3, and we have this temperature is equal to delta H0 minus T, If we include this part, then we come to this equation. T is equal to delta H0 plus P into delta V0 plus this term, which is 2 into WF FEMG olivine into 1 minus 2XFE olivine minus WFEMG OPX into 1 minus 2XFE OPX, and then you divide it by del S0 minus 2R ln XFE by XMG orthoperoxine divided by XFE by XMG olivine. And remember, this is our Kd value. Now you see here, last time this term was not there, and we saw that essentially for a particular composition this right side was constant. Now we have added this one to account for any amount of excess mixing over and above the ideal mixing. Now this is a compositional term. This is a compositional term. So what happens, those straight lines that we did, they were independent of composition. You remember your T value was equal to exponential minus 1 by 2R T, exponential minus 2R, and then del H0 minus it is something like this now. Wait. It was ln or XFE by XMG OPX is equal to XFE by XMG olivine exponential minus 1 by 2RT into del H0 minus T del S0 plus P del V0. That was how the expression looked like. Now here it's important. This term under exponential, if you take ideal exchange, this term under exponential does not include any compositional term. It only is a variable of pressure and temperature. So what happens for a particular temperature value, P del V is a very small value. For a particular temperature value, this part is a constant. And this part being constant, so you have a straight line equation. But here, if you do the same expression, if you do the same expression here, if you want to do it, this will be like this. This will not end here. This will not end here. Instead, you will have this type of a situation. Plus WFEMG olivine into 1 minus 2XFE olivine minus WFEMG OPX into 1 minus 2XFE OPX. That is how it would be included, and you will have a third bracket and then a final bracket. So this is how it will be. If we include, if the system is not ideal. So in that case, you can see, if you put in a temperature value, this expression is not a constant anymore. It's not a constant anymore. So what it will do is, it will not obey a straight line passing through the origin, the simplistic way of a straight line passing through the origin. It will not be, because then this term will be also a function of composition. Okay, so you will not have a straight line fit, you will have a curved line fit, and that is a major problem, to fit a curved line through this expression. So it's not very convenient when the exchange, iron magnesium exchange, or any cation exchange in a reaction behaves strongly non-ideally. If such a case arises, then the straight line assumption that we considered before for ideal exchange, that falls through. You don't use it. Then you have to use it the normal way to find out the pressure temperature condition by simultaneous solution of the exchange reaction and some other reaction. That is possible. Now a little more, this is how you will find out, estimate temperature and pressure. Just one thing I would like to add, because I want to give you this paper by Ferry and Spear. I think you need this little information for you to understand the paper. Those people actually, Ferry and Spear, does what is iron magnesium exchange between a biotite and a garnet. All these parts you read up, you remember what I said. It doesn't talk about iron magnesium exchange between olivine and orthoperoxide. It talks about iron magnesium exchange between biotite and garnet. What they do essentially, it's very crucial, it's a very pivotal paper in metamorphic petrology, determinative metamorphic petrology. They take, their assumption there is an ideal exchange. Their assumption there in that paper is ideal exchange of iron and magnesium between biotite and garnet. So in their expression, this is not there. That means there is no non-ideality term. It's an ideal exchange reaction. So they don't have this term. They don't have it. So they have this term del H0 plus P del V0 and del SR and what is called KD term. When you read the paper, you will see it. Just remember what I told you. You have a KD term. Now, I have always been telling you, just to avoid any complications, that all these terms, these thermodynamic terms, all these thermodynamic terms are known, either experimentally or theoretically. But I did not tell you. I was only speaking a half-truth. I was not speaking the full truth. The situation is like this. When Ferri and Spear did their experiment, these terms, enthalpy and entropy, these two terms were not known very strongly. Even now, if you see different estimations of this, there is a lot of problems, which is, I don't think it's necessary to discuss at this point, the natural samples, synthetic samples, order, disorder. We don't have to go into this complications. But when Ferri and Spear did this great paper, which has been huge citations, these two terms were not known. These two terms were not known. So essentially what this term is, say for example, I will just write the biotite garnet exchange, and then I will discuss it. It's better. Otherwise, you may not appreciate it. Their equation was, reaction was, and I don't have the paper with me, Fe3Al2Si3O12 plus KMg3AlSi3O10OHO twice is equal to Mg3Al2Si3O12 O10OHO twice. Oh my God, what am I doing? O12 plus K Fe3Al Si3 O10OHO twice. That's the equation they took. It doesn't matter whether I write this side here or this side here, because essentially I'm talking of an equilibrium. You can do, so long you have written the reaction, it's done with. You can put this on this side or you can put this on this side. It doesn't matter. You're referring to the same equilibrium. So it doesn't matter. Maybe in the paper you will see this is written to the left and that is written to the right. It does not matter at all. So what is important is, here you have iron, garnet, magnesium biotite. Here you have magnesium garnet, iron biotite. So essentially it's an iron-magnesium exchange between garnet and biotite. And what they did was, they were trying to find out a thermometer like we have done, and it is an ideal exchange thermometer. They don't take in non-ideality into consideration. Their paper was dated to be 1978, although non-ideality, etc. were all well taken care of. But in their thermometer, because there are certain limitations, they did not take the non-ideality effects into consideration. So they had an ideal exchange situation. And what they did was, they did experiments. So in those experiments, they produced a biotite of a particular composition and a garnet of a particular composition. Say, for example, it's not there in the paper, I'm just telling you. They say formed a garnet, they had a garnet, which was, say, almandine 80. Means what? They had, it was an FEMG binary, almandine 80. Say you have a garnet at almandine 80. Right? That means XFE garnet is equal to 0.8 and XMG garnet is 0.2, both adding up to 1.0. They synthesized a garnet, and this garnet was quite large. They also synthesized, naturally, biotites. And these biotites, flaky biotites, these were grains were small. nice tillage, small. And maybe they have a biotite. They did not know what was the composition of iron biotite or so. And so say calculated an XFE biotite, say equal to 0.5. That means XMG biotite is equal to also 0.5. Now this is called, Fe biotite is called anite, and XMG component of biotite is called phlogopite. It's called phlogopite. They took a garnet and they took biotite grains. These biotite grains were very small. Were very small. These grains were small. And this grain was large and big. And then they put these two minerals together. They put these two minerals in contact and they changed the temperature. So they had taken the temperature at, say, I think they did their experiments at 2.07 kilobars. 2.07 kilobars means into 1000, so 2070 bar. That was the pressure they took for the experiments. And the temperature they took, say for example, they equilibrated this at, say, 800 degrees centigrade. So 800 degrees centigrade and P was 2070 bar. 800 degrees centigrade and 2070 bars. This was the PT condition of, say, one of their experiments. And what they did was bring this biotite in contact with the garnet. Bring this biotite in contact with the garnet, and the garnet is very large and the biotite is very small. So what happens when you heat it, the iron magnesium exchanges between biotite and garnet. Okay, but the garnet being very large, so it acts like a reservoir of XFE and Mg in this ratio, being very large. So it's like an ocean, and the biotite is something like a small river flowing into the ocean. So what happens is, so the garnet really, both the garnet, but the biotite changes its composition. So that at that particular temperature and pressure, remember, T del S, P del V, at that temperature and that pressure, at that temperature and that pressure, the biotite equilibrates with the garnet, not the other way around. Not the other way around. The biotite equilibrates with the garnet. That means there is magnesium ion exchange between the garnet and the biotite. And obviously, because this is a very large reservoir and this is a very small grain, any change in the garnet composition will be very small. But the biotite being small, it will quickly re-equilibrate to the composition at which the garnet is at this particular pressure temperature condition. So the biotite composition, this composition will change to the new equilibrated composition. Have you understood? So this composition will not be. The composition will be, this is the starting material. But when you end the experiment, the biotite will have a composition different from this, because this garnet at that pressure temperature, if it is to be equilibrated with biotite, it has to be equilibrated at that pressure temperature condition. Right? So they give you a table, which you should, when you read the paper, essentially you will be reading the table. So you start with a material, which is called the starting material, and then you have temperature and pressure, and then you have a material, product material biotite, which is very different from the composition of the starting biotite, of course, because the biotite changes its composition with respect to the garnet. And Ferrier and Spear did not have any way to find out how the biotite, what should be the biotite garnet composition in equilibrium. Right? So what they did was, when you read the paper, you will see there is a table. And so what happens was that you take a temperature pressure condition, and they found out, say for example, at this pressure, 2.07 pressure, and at this temperature, they have a particular XFEMG value of biotite garnet. They took another temperature, and another temperature, and another temperature, and another temperature, and everywhere they took garnet, and then you have the product biotite, which actually is a run product. That is, these are equally braided assemblages. So his data it had temperature at a particular temperature, then it had a particular pressure, it had a particular composition of XFE garnet, and it had a particular composition of XFE biotite. Remember, this is the product biotite, not the starting biotite. But XFE garnet is the starting garnet, or even it could be the product garnet. It does not matter, because the garnet is very big in comparison to the composition of biotite. So the garnet can be taken to be having the same composition, whether it's a starting material or a product. But the biotite, you take the product value. So you have temperature, pressure, XFE garnet. So you also know XMG garnet. And you have XFE biotite. So you have also know XMG biotite. But why was it doing all this? He was doing for a very specific reason. You can understand here, the exchange reaction can be written as del G Pt of the reaction is equal to, at equilibrium it should be equal to 0, and then you will have del H0 of the reaction minus T del S0 of the reaction plus P delta V0 of the reaction plus, now you see, 3 RT ln. Okay, I'm jumping steps. Maybe I should write it like this. Then RT ln activity of iron in biotite into activity of magnesium in garnet divided by activity of Mg in biotite divided by activity of iron in garnet. This is the equation of state. This, if you take an ideal mixing solution, ideal exchange, there will be no gamma terms. The gamma term should be equal to 1. Gamma terms are 1 because W0 values, interaction parameters are 0. So essentially this expression boiled down to 0 is equal to del H0R minus T del S0R plus P into delta V0R plus, you see what is activity of biotite? In this expression, is equal to XFE biotite into gamma Fe biotite and then whole cubed, right? But gamma Fe biotite is equal to 1 because it's ideal exchange. So what he did was, this reaction for, you have XFE biotite whole cubed. So all of them will have it, and this will become 3RT ln XFE by XMG biotite divided by XFE by XMG garnet. Remember, this is KD. This is KD ideal. Now, you may find in the book, this KD is written differently. It does not matter. It does not matter. You take the paper, read the paper, and do the derivation systematically. You will see where it comes to. Now, so what is happening at this point of time is, here, for more or less, for 99.9 recurring percent, the delta V0 value, you see, you see what is delta H0 for this reaction? Delta H0R is equal to H0 Fe biotite plus H0 Mg garnet product minus H0 Mg biotite plus H0 garnet, and this is Fe. This is what you get. Remember, this will be equal to 3. No, this is what it will become. So this is enthalpy of anite in biotite plus enthalpy of pyrope in garnet, that is the product, minus H0 Mg phlogopite of biotite and H0 Fe garnet. So in order to find out del H0, you need each of these terms. You should need each of these terms. Similarly, if you want to find out del S0R, you have to do the same thing for entropy. You have to know each and every phase compound. But at that time, these values were not known. Neither the enthalpy nor the volume, nor the entropy. These two terms were not known. So essentially, there was a difficulty in calculating these two terms, del H0R and del S0R. These were the two terms which was difficult to calculate, because at that time experiments did not determine these values. But the volumes of anite, pyrope, phlogopite and albandine, they were known. They were known. They were given in centimeter cube. They were given in centimeter cube, molar volume. Those were determined. Those were available. Mostly all are available. But the problem was, these two were not available. But other terms were available, just like, for example, temperature was available from the experiment, pressure was available from the experiment, delta V was available from known molar volume data, temperature was available, and these terms were all available. And these terms were all available. What was not available is this. So what they did was, the argument was, what you need from the reaction is delta H and delta S. You don't need individual enthalpy and entropy value of the phases. You don't need. You need the enthalpy of the reaction and the entropy of the reaction. The change, you need delta values. You don't need initial values, which was not available. So what they did was, they wanted to calculate this. So how do they calculate? I'll show you. So in this expression, you can write remember what y is equal to mx plus c is the equation of a straight line. So what he did was, you see, at the conditions of the experiment, pressure, what are the conditions of the experiment? Pressure, temperature, XFE garnet, which means XMG garnet, and XFE biotite. These are known. So this term can be completely known. This is known. This term is known. So what you do essentially is, and in this part, what is unknown? Temperature here is unknown. This temperature here is unknown. So if we take the temperature as the x-axis, if I take the temperature as the x-axis, so if I do this, say I write this expression as phi. Let's say I write this expression as phi. So it becomes delta H0 R is equal to T into delta S0R plus phi. Have you understood? Delta H0R or no. Sorry. What I do is I write this as what I will do is I am actually telling you the paper. What I will tell you is here you plot phi versus t. If you plot phi versus t, say for example if this is t and this is phi, for the experimental conditions given in Ferrier sphere, you will see that you have several points determined. Have you understood? Several points you can determine by plotting phi versus t. Remember to take temperature as kelvins. Remember, take temperature in kelvins. And this is phi versus t. For a particular t, you will get a particular y. Change the t, you will get another phi. Change the t, you will get another phi. So you will have a variation of phi versus t. Now, if you draw a line through this is called linear least square f. This is called linear least square fit. What does it mean, linear least square fits? That means, say for example, if there is an x and there is a y and there are 3 points. So you draw a straight line such that the perpendicular distances, do you understand? The square of the perpendicular distances, the square of the perpendicular distances is the smallest. Have you understood? If it is 0, then all the points lie on the straight line. If all the points, you see, you take this perpendicular distance from the point, perpendicular distance from the point, perpendicular distance the same. So it's the squares. And you take the least value out of it. Okay? That point which gives you the least value for the sum of squares, that value is a point of the straight line. From this, you can calculate the straight line. This is also known as linear regression. Okay? So now, once you do this, then this reaction, I'm not telling you, you have to find it out. Then this equation has a intercept and it has a slope. It has an intercept and it has a slope. Now, I will not tell you more. I will tell you that one you will have, if this line is, straight line is there, then it will have an intercept which is C and it will have a slope which is M. Okay? If it's an intercept, it will have a slope and an intercept. So, and you have delta H0R and delta S0R. You can see the one which is T here, the delta S0R is here. So, if you find the slope and find the intercept, you will be able to find the entropy and the enthalpy of the reaction. So once you have found out the enthalpy and entropy of the reaction, the rest is known. So you can use it now as a thermometer. How? You can use it as a thermometer. How? It's the same like I did before. So you have temperature is equal to delta H0 plus P into delta V0 divided by delta S0 minus R ln Kd. This should be 3. So now, once you have found out the slope and the intercept, and therefore delta S and delta H, you should be careful how you find out, and be careful about the sign. I won't tell you everything. So, you have found out now this, you have found out now this you already knew, and so if you put the compositional values here, you will be able to find out the temperature as a function of pressure. As I told you, it has a very small volume. Now just a little careful with the in thermodynamics part, and this I want to alert you before you go into something. In the paper, enthalpy is in joules per mole. The entropy, you know, this is free energy term. This is joule per mole. This one, del S0R, should be joule per Kelvin per mole. This should be joule per Kelvin. You see, joule per Kelvin. Okay, this should be in joules. This should be in joules per Kelvin. So, by Kelvin into temperature, which in Kelvin should give you joules. Now, this pressure term and this volume term. This pressure term is in bar. And this volume term, this in joule per bar. So, you see, joule divided by bar into bar. So, you get joule. Here also R is in joules per Kelvin, and the value is 1.98717. Sorry, I made a mistake. Oh God. The calculations in the paper, was, I have calories, this is not joules, calories, this is calories per Kelvin, and this is bar, of course. And this is calories per bar. This is calories per bar. This is bar. This is calories per Kelvin. This temperature is Kelvin. The temperature is Kelvin. And this enthalpy is Kelvin. And R is in not joule per Kelvin. The R value is equal to 1.98717 calories per Kelvin. So this is the universal gas constant. In joules it will be 8.3143. You have to multiply it by 4.184. That's all what you have to do. From joules to calories. So now you read the paper and you try to do the regression. These regressions you can do by Excel spreadsheets. Try to read the paper, take time, try to understand the paper, and therefore you can find out you can try to reproduce the numbers that they have given for the thermometer. They have given del H value, delta S value, they have calculated, they have given it there. So you try to get that value. So what these types of calculations where you don't find things independently, you don't find enthalpy of this phase component, enthalpy of this phase component, enthalpy of this component. What you do an experiment, like I have said before, and from this you retrieve enthalpy and entropy values. So what happens is, these are called retrieval calculations. So these are very important for thermobarometry. It was very fashionable to do thermobarometry quite some time back, but after that it has now, with PT pseudo sections and all, it has not lost its sheen, only thing it is used much less. But quantitative metamorphic metrology started basically with quantitative thermobarometry. A lot of work has been done since then. So I won't pick up the next topic because that will take us far beyond what we have. So I will stop here for today, and next class we will see how we can go from. So what I have shown you is to find out temperature and to find out pressure. How you calculate temperature and calculate pressure, and you can find out pressure and temperature of the rock for the equilibrium assemblage. You can find out the pressure and the temperature value. These are the two things that you need to find out first. Once you can find that out, a lot of new things can be calculated, and this I will show you in the next week's lecture. But for this lecture, I think you should go through this. If there are any mistakes, you please correct them, like last time you said, and I agreed with it. So there is nothing to mug up here. It's just pure derivation. Before I close this topic, I will just give you one clue for activity, because sometimes people make this mistake in calculating activity. I will tell you why. Okay. Let me take an exchange reaction between, say, MgFe exchange reaction between olivine and garnet. Olivine and garnet. So if you do that, then you can write the expression as Mg2SiO4 plus Fe3Al2Si3O12 is equal to Fe2SiO4 plus Mg3Al2Si3O12. Now, before doing anything, what you need to do is balance the reaction. You see here Mg2, here it is Mg3. If you have to balance it, you have to multiply it by 3. And here you also have to multiply by 3. But then, if you have to multiply this one, then you see, you have to multiply this by 3 into 2, 6, and you have to multiply this by 2. But if you do this, then you see your aluminium here is 2 into 2, 4, but here it stays 2. So in order to balance it, you have to multiply this by 2 and this by 3. So this is a balanced reaction. Have you understood? I will tell you why I'm writing this. Here is the 3, and here is the 3, here is the 2, and here is the 2. Right? Now, when I write an exchange equation of state, then I write 0 is equal to del H0 minus T del S0, I'm simplifying it, plus P delta V0 plus RT. Now is the word of caution. Now is the word of caution. Activity of Mg in garnet, but then you should have a square. This square is because not of the site, but because of the stoichiometry. Have you understood? Because of the stoichiometry. So, and here next will be activity of Fe in olivine whole cubed because of the stoichiometry cubed. And then again at the division sign, activity of Fe garnet whole squared, stoichiometry. This has nothing to do with mixing, this is the stoichiometry. And then activity of Mg in olivine, and this is cubed. Have you understood? This is cubed. Now if from this one you can write RT-ln, if I remove activity to activity into activity coefficient, what is, okay, let me tell you. So what will be activity of Mg in garnet will be equal to xmg in garnet into gamma mg in garnet into whole cubed. Have you understood? Activity of Mg in garnet here is xmg in garnet into gamma mg in garnet. That is how you break up activity. And this cube is mixing on 3 sides. This is also true for activity of Fe in garnet is equal to activity of xFe in garnet into gamma Fe in garnet into cubed. But if you take for olivine, then you see activity of Fe in olivine is equal to xFe in olivine into gamma Fe in olivine, and this is squared because the mixing is on 2 sides. Here, similarly, for activity mg. So when you do this, what you get is RT ln x mg garnet into x fe olivine divided by x fe garnet into x mg olivine, and this should be 6 here because it's 2 into 3. For this, it's 2 into 3. For this, it's 3 to 2. So this is 6 RT plus 6 RT ln. Now, gamma mg in garnet divided by gamma fe in garnet, and then gamma fe in olivine and gamma mg in olivine. That's how it is. So you see, here you get 6. Why 6? It is because here this 2 value and 3 value are because of the stoichiometry. It's twice. But when you break up the activity, then it takes into account the mixing. So the mole fraction, if you take it, the mole fraction actually is to the power 2 to the power 3. So it's to the power 6. xmg to the power 2 to the power 3. And for xmg garnet, it's xmg to the power 3 to the power 2. And for xfe olivine, it's to the power 2 to the power 3. So it's always 6. Be careful of this. It is when you write activity term, you have to take in the stoichiometry. But when you break up the activity into mole fraction of the activity coefficient, then you have to take the number of sites on which mixing occurs. Right? Good. So now you read, I will post it to you, and you read the paper and try to derive back the equation. Right? Thank you.